Smoke rises from the mountain of doom. The hour grows late, and Gandalf the Grey rides to Isengard seeking my counsel. For that is why you have come, is it not, my old friend? I see you have chosen the way of pain. Well, that was kind of silly, folks. I apologize. This is the staff of Saruman that my son Nate made for me once for my birthday. So brought it out of my office and thought I'd use it as a toy. Today's lecture is actually one of my favorites because it's something that I did a lot in grad school, and it's something that we do in my lab all the time. We've talked about peptide structure and function, but now we're going to talk about how chemists actually make peptides in the first place. So let me go ahead and share my screen with you. We'll turn to Notability, and we'll get started. All right. Long ago, we talked about how to make amide bonds. And recall that we said, and actually this was a problem on exam 2, we said that in order to make an amide bond between an amino group and a carboxylic acid, we needed some reagent that could turn the OH into a good leaving group that does not have an acidic proton. The danger here is that if you use an acid to try to turn the OH into OH2 as a good leaving group, you're going to protonate the basic amine. I should point out that making the amide bond is a dehydration reaction. You're losing water. And the reagent that we use for this process is called DCC. DCC stands for dicyclohexyl diimide. And if you hear yelling in the background, that's just my boys having a little too much family togetherness. The structure of dicyclohexyl diimide is a carbonyl carbon with an oxygen here. Actually, I'm wrong. With a nitrogen here, another nitrogen there. Oh my goodness, folks, I am so sorry about that. Distraction is great. Dicyclohexyl carbodiimide involves a carbon doubly bonded to two nitrogens, and each of those nitrogens are bonded to a cyclohexene group, or cyclohexane group, abbreviated as CY. We didn't learn the mechanism for this reaction. We could talk about it, and I could show it to you just for completeness so that you can understand how this reaction works. First, you need a base to remove the proton from the carboxylic acid. It's possible that that base is the amine. It's possible that base is another intermediate further down in the process. Once you've removed the proton from the carboxylic acid, it becomes a decent enough nucleophile to attack the carbonyl carbon, the imide carbon rather, which is reactive very much like a carbonyl carbon. And at this stage, lone pair electrons would move on to the nitrogen, but a negatively charged nitrogen is really, really, really unstable. And so probably instead of drawing arrows to the negatively charged nitrogen, probably as that step is happening, we pick up an acid from we pick up a proton rather from whatever the conjugate acid of our base was from the previous step. Having done that, we've made a new oxygen-carbon bond. Here's the carbon. Here's the doubly bonded nitrogen. And here's the singly bonded nitrogen. And I'm going to just write the CY by the nitrogen, and you can understand that CY here equals a cyclohexane ring. Now you have converted OH into something that has no acidic proton. All right. A group that has no acidic proton and can be a decent leaving group under the right conditions. So no acidic proton and a decent leaving group. It may not appear to be a decent leaving group now, but I'll show you in a future step why that's the case. All right, so now if you look at this molecule, it looks a little bit like an anhydride. An anhydride is like an molecule like this, where you have a carbonyl carbon that's bonded to another carboxylate group. And we've got that same kind of structure here. Here's a carbon-oxygen double bond, here's an oxygen, and here's another carbon heteroatom double bond. So this intermediate has anhydride-like reactivity, just as we saw way back in chapter 22. Things that are anhydride-like in reactivity or acid chloride-like in reactivity can be attacked directly, even if your nucleophile isn't negatively charged. So we can have the neutral nitrogen attack the carbonyl carbon to give us a tetrahedral intermediate, which we will draw. All right, that may be a little bit unusual. Maybe you're not, and I guess we're missing the negatively charged oxygen. That may be a little bit unusual. This is the same thing as though we had drawn the tetrahedral intermediate in the following way. Sorry, we're missing an R prime there. And feel free to skip ahead during these boring moments when I'm still drawing things, unless you're also drawing things, in which case you can stay right with me. I sort of need elevator music for that part. Maybe I'll start providing it myself. So this is our tetrahedral intermediate. And we've got two things that need to happen. We want the nitrogen to stay. Unfortunately, the nitrogen is protonated, so it could readily get kicked off. Second, we want this group, the oxygen, the carbon, and the two nitrogens. We want that to leave, but if it left, we'd have a negative charge on the oxygen or on the nitrogen, and that would be somewhat unfavorable. Less favorable, certainly, than to kick off the neutral amine. And so we've got to do something to keep the nitrogen there and to turn the green group into a better leaving group. Maybe it would be helpful if I highlighted the purple stuff over here as well. And the green stuff. All right. So what's going to happen here is lone pair electrons on the nitrogen are going to kick down and kick off the oxygen. Maybe I can show that happening, I don't know, on the other side. At that stage, the electrons in this carbon-oxygen bond will leave and go on to the oxygen, though actually instead of staying on that oxygen, they will kick down to form a new oxygen-carbon pi bond. At that point, the carbon-nitrogen pi bond will break, and the nitrogen will reach over to a proton on the purple nitrogen that's positively charged. That's an intramolecular six-membered ring type process. And actually, maybe we'll show pi bond attacks nitrogen, and electrons go back onto the nitrogen. And what we're left with at that point is the desired amide product. And instead of water, we have the following molecule, which carries the two protons and the oxygen that would have been in water, but has them attached to this very stable molecule. Okay, remember I said that forming an amide bond is a dehydration reaction. Here is an oxygen, and here are the two protons that we got. It's this oxygen, that proton, and one of the two protons on the amine that we lost. Okay, and this is this green leaving group is a byproduct that is easy to get rid of, and we've made a new amide bond. Another word for amide bond is peptide bond. This reaction to link an amine with a carboxylic acid is often called a coupling reaction because you're coupling those two things together. And DCC is often called a coupling reagent or an activating agent. It turns the carboxylic acid from something that wasn't very reactive into something that has anhydride-like reactivity, and is electrophilic enough for the amino group to attack and then give you the amide bond. This is a mild way of making amide bonds. Of course, you could argue, why don't I just make the acid chloride and then make the amide bond? Wouldn't that be easier? In principle, yes. Though acid chlorides are very unstable, you can't store them for long periods of time, and they're subject to other issues as well. So it's easier to just use the carboxylic acid and then the coupling reagent along with the amine to make your new amide bond. All right, so that's basic amide bond forming chemistry. There are lots of different coupling reagents. We'll continue to use DCC, and then maybe further on at the end of this lecture, I'll show you how we do this chemistry in my lab. So this is great. Now let's think about how this applies to making amide bonds in peptides. And let's think about, let's remind ourselves of what a peptide is. Remember, a peptide is an oligomer of amino acids. You have the backbone nitrogen, the alpha carbon, and the carbonyl carbon. Whoops. And that pattern repeats itself. Each amino acid has a nitrogen, an alpha carbon, and a carbonyl carbon. And so we continue on. Maybe I'll finish drawing this tripeptide, and we'll be ambiguous about what's on either end, and the side chains don't all have to be the same. Actually, let's just say that this is a tripeptide, and it's under physiological conditions, pH 7, so the C-terminus is negatively charged, the N-terminus is positively charged. Suppose we wanted to make this tripeptide. Let's think about the challenges that we have here. What if I were to take amino acid 1 and amino acid 2, and what if I were to try to link these together with DCC? Do you see a problem? Okay, go ahead and think for a minute and see if you can see a problem. I'll make some elevator music. Dun, 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 dun. You can just cycle through that a couple of times if you need more time to think. Suppose my target molecule was just to have the following dipeptide after this first reaction. And actually, we can go back and erase amino acid 3 since we're being... And we can assume we've got the Zwitter ionic form of the peptide at the end. That's fine too. If this were our target molecule, where you have side chain 1 at the N-terminus and side chain 2 at the C-terminus, do you see any particular problem here? And if you thought about it, not only would you get the product I had shown you, but you would also get undesired products in which you bonded two R1 amino acids together, and then you would get shrink that down a little bit. And then you would get another possibility, perhaps where the R2 side chain had been established first, and then the R1 side chain at the C terminus. Or you might even get the version where both side chains were R2. And then you might actually get tri and tetra peptides as well, depending on how much DCC you used. In other words, we have no, regioselectivity, because the purple amine can react as easily with the green carboxylic acid as it can with the orange carboxylic acid on another molecule. And that's, and at the same time, the pink amine can react with the green carboxylic acid group on another molecule just as easily as it can react with the orange carboxylic acid group on the R1 amino acid. Let's just make that clear by labeling the connections we see. In this first target peptide, we have a connection between the pink amine and the orange carboxylic acid group. In the one to the bottom, we have a connection between the purple amine and the orange carboxylic acid group. Over here on the right and up top, we have a linkage between the purple nitrogen and the, green carbonyl group. And then we also have a connection between the pink nitrogen and the green carbonyl group. In other words, we don't have any selectivity, and that's the problem. So in organic chemistry, when we can't develop selectivity for a particular process, our solution is to use protecting groups. Now, you've seen protecting groups before. We used the TBDMS group for alcohols. We used acetals for either alcohols or ketones or aldehydes, depending on, that's not how you spell aldehyde, depending on the process, the situation. And I think those are the two protecting groups we've encountered so far. We are going to need a new protecting group, PG, for carboxylic acids that will mask them and prevent them from being reactive with the DCC reagent. And we're going to need a new protecting group for amines. And ideally, these two protecting groups should both be stable to the DCC conditions, but individually they have to be removable under distinct and or orthogonal conditions. What that means is, if we want to remove the amine protecting group, we want the, if we do that, we want the carboxylic acid protecting group to stay in place. So I'll introduce the new protecting groups that your text has. The protecting group for a carboxylic acid, and there's actually a few of these, but the most convenient one that your text uses right now is the so-called benzyl ester. And it comes from the fact that you've got this benzylic carbon attached to the oxygen of the carboxylic acid, and we will abbreviate this, as we do often with protecting groups, as OBN. This protecting group is stable to DCC conditions. It won't come off. Under DCC conditions, you can install it easily on a carboxylic acid by first deprotonating the carboxylic acid. Well, you can install it by deprotonating the carboxylic acid and then using a very stable reagent called benzyl bromide. And the mechanism here is just an SN2 mechanism, and that will give you the benzyl ester. Of course, if you wanted to, you could make this ester from the carboxylic acid and benzyl alcohol under acid catalyzed conditions. In practice, this protection reaction is the one that is most often used to make the benzyl ester protecting group. Okay. One of the characteristics of good protecting groups is that installing the protecting group is a high yield reaction, and you want this to be about 100% yield. So the protecting group goes on easy. The next key is the deprotection reaction easy. And you could remove this ester protecting group using an excess of water in the presence of acid. But we're going to see that the protecting group we will use for the amine is acid sensitive. So acid catalyzed ester hydrolysis would be a pretty bad idea. So what we will do instead is what scientists have discovered about benzyl esters, is that the bond between the ester oxygen and the benzylic carbon can be broken under palladium catalyzed hydrogenation conditions. Basically, we're going to add And what I'm going to show you isn't necessarily what goes on. Remember, this is catalyzed on the surface of a metal. But basically, you're picking up a proton here and adding a hydride there, or vice versa. In the end, you end up with the carboxylic acid, and then the other thing that's left behind is now just plain old toluene, which is a solvent in which you can remove in a fairly straightforward way from your carboxylic acid. So the deprotection reaction is actually called, because it involves breaking a sigma bond under palladium catalyzed hydrogenation conditions. We'll call this hydrogenolysis instead of hydrogenation, because you're using it to break a sigma bond. And this is, again, very easy to do. And in practice, the yield is about 100%. What you do in these reactions is that you have a flask, you have a round bottom flask that contains your material. Your palladium catalyst is there at the bottom. In the solution, you have your molecule in solvent. You have a rubber stopper here, a needle going through the rubber stopper, and then attached to the rubber stopper is a balloon that is full of hydrogen. And when you are done with the reaction, which you monitor by TLC, you simply take the balloon off, filter the solid palladium carbon catalyst out, and let the liquid pass through, and then you can concentrate the liquid to isolate your product. So it's a very, very clean reaction. All right, so that's going to be our protecting group here for the carboxylic acid. Let's talk about the protecting group for the amine. Again, the requirements are it has to be stable stable to DCC, and it has to be stable to hydrogen and palladium on carbon, and has to come off under, has to be easily removable under orthogonal conditions. All right, so the protecting group of choice for the amino group is called Bach. What is the chicken's favorite protecting group? Bach. Bach, 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 Bach. Sorry, terrible humor. So let me show you the protection reaction. You start with your amine. Sort of spanning a page here. You start with your amine. You add a reagent called Bach anhydride. That will often be abbreviated in your text as Bach2O. Bach anhydride is another name for it. Basically, you've got a carbonyl carbon here, and you've got what you may not recognize as a good leaving group here. And I'll show you why that's a good leaving group in just a second. So the nitrogen, because this is reactive like an anhydride, the nitrogen attacks the carbonyl carbon to give you a tetrahedral intermediate. I'm going to skip the proton transfer step and go right to the intermediate where our nitrogen is attached to the carbonyl carbon. And through a series of simple mechanistic steps, we're going to trade one negatively charged oxygen for another. So electrons kick off. They kick off this oxygen, but instead of the electrons going on to the oxygen, they come here to make CO2, and then this group leaves. And the driving force for this reaction to happen is that CO2 leaves and entropy dramatically increases. So here's my amino compound, here's CO2, and here is T-butoxide, and maybe that's the thing that rips off the proton from the nitrogen in the previous step. Ultimately, this becomes T-butanol, which is a solvent and which you can readily isolate. This group here on the nitrogen is the Bach group, the functional group where you have one oxygen, or rather a carbonyl carbon that's involved with an ester on one side and an amide on the other. That functional group is called a carbamate. And we'll abbreviate this protecting group as Bach, NH, and then whatever else is attached to that nitrogen. Some people will call this T-Bach to stand for the T-butyl group. Bach stands for tert-butyl oxycarbonyl group. Tert-butyl oxycarbonyl group. And there's no other kind of Bach group, so I just dropped the T. The Bach group is stable to hydrogenolysis and is stable to DCC, but it is, and the installation here of the Bach group again is about 100% yield. It's very easy to do. It happens very quickly. So that's the protection reaction. The deprotection reaction is also easy. The Bach group comes off readily in strong organic acid. And the acid of choice is frequently trifluoroacetic acid, which is more acidic than acetic acid due to the neighboring fluorine groups. We'll often abbreviate that as TFA. So the Bach group gets removed, the amine is released, and usually as the ammonium ion. We lose CO2 and we also lose tert-butanol. The mechanism for Bach deprotection is interesting. It's similar to the mechanism of the Bach protection reaction, though the deprotection reaction relies on the fact that the tert-butyl group can make a decent carbocation. I should add that these conditions happen in like 95% TFA with 5% water. So what happens is that in TFA, we protonate the nitrogen within the Bach carbamate. We do that with our strong acid. And then at that point, electrons from this carbon-oxygen bond between the T-butyl carbon and oxygen swing down to form a new oxygen-carbon pi bond, and that makes CO2. And then these electrons on the nitrogen leave, between the carbon and the nitrogen, go back on the nitrogen. And in fact, if we want, we can just show these as the electrons that pick up the proton from Bach, or pick up the proton from the strong acid. At that point, we would have T-butyl cation, we would have CO2, and then we would have our amino compound. The amino compound likely gets protonated via another step. Likely the carbocation gets picked up by water, and then after a deprotonation reaction, that gives you the tert-butanol. So this reaction is fast, it's 100%, and it's irreversible, because once you've lost the CO2, you're gone. And that's actually how the protection reaction was. It was fast, 100%, and irreversible. Okay, so we can install Bach. We can take Bach off under conditions that don't bother the benzyl ester. We can install the benzyl ester and take the benzyl ester off under conditions that don't bother the Bach group. So let's show how this might apply to a synthesis. Suppose I wanted to make the amino acid ilk. All right, suppose I wanted to make the tripeptide ilk. All right, here's how I might start. I might start first with, and I'm going to show the amino acids in their neutral form. Chances are you buy them in their zwitterionic form. Either way, it doesn't matter. Here's isoleucine. Notice that this is the N-terminus of my peptide. This is the C-terminus. Peptides are always written from left to right in the order N to C. Always, 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 always N to C. So I know that in this bond between I and L, I need the carboxyl group of I to bond with the amine group of L. So first, I'm going to want to protect the nitrogen as the Bach group. So I'm just going to use Bach anhydride. Sometimes you need a little bit of a base, but we're going to pretend that that's not an issue. And that will turn our amino acid into the Bach protected version. In practice, you would buy the Bach protected amino acid, but there you go. Second, I would need to take the amino acid leucine, and notice that I'm going to need to have a bond between the carboxylic acid group of isoleucine with the amino group of leucine. So here's the leucine structure. I'm going to want to keep the amino group unprotected while protecting the carboxylic acid group so it doesn't interfere with the reaction. To do that, I'm going to use benzyl bromide. You can abbreviate it like that. We might need a base, but we're not going to worry about it. That will install the benzyl ester, which I'm again abbreviating. Now the amino group on our isoleucine is safe and protected. Also, the carboxylic acid group on our isoleucine is safe and protected. I don't know what color we ought to have used. Maybe red for stop, or on the other hand, maybe green for go ahead and ignore it. Go ahead and pass it by because it's protected. Maybe we'll stick with that. And so now we can actually take these two groups together and use DCC, and that will enable us, sorry, that arrow went kind of in the wrong place. That will enable us to make the isoleucine leucine dipeptide with the N-terminus protected as the Bach group and the C-terminus protected as the benzyl ester. And I will just draw that out for you. I won't draw the Bach protecting group, but here's your isoleucine, and then here's your leucine amino acid, and here is your protected C-terminus protected as the benzyl ester, and then the N-terminus is protected as the Bach carbamate. let's see. I'm going to call an audible here, and we're going to choose an amino acid that's different from lysine for reasons we can talk about later. Let's just choose alanine, so ILA. So now we need to make a bond between the carboxylate group of leucine in the dipeptide with the amino group of alanine on the other side. So first, I guess this was our third reaction. Our fourth reaction is going to be to take alanine, oops, wrong stereochemistry. I'm going to take alanine and we're going to use benzyl bromide to protect the alanine carboxylate group as the benzyl ester. And then we're going to take the dipeptide, and now we need to make it so the carboxylate group is free. So we'll do the deprotection reaction, hydrogen and palladium on carbon for the dipeptide, and that will get us the following molecule with the carboxylic acid group open. Notice we still have the N-terminal nitrogen protected as the Bach group, but now we have removed the protecting group, so the C-terminal carboxylic acid group is ready to go. We can now take these two amino acids and using DCC, we can make the new amide bond between the carboxylate group of leucine and the amino group of alanine, and that will give us this protected tripeptide. And then, since in many cases for specific applications, and in particular natural product synthesis and making peptide drugs, often you don't want the protecting groups there in the end. So we would need to do the benzyl ester hydrogenolysis and the TFA, and the 95% TFA in water, and that will fully deprotect my peptide. There we go. And my amino group will likely be the ammonium, positively charged ammonium ion. My C-terminal carboxylic acid group will likely be the negatively charged carboxylate, and that is my tripeptide ILA. Now, that is one way. Let's see, so 6, and then we had 7 and 8. So that was quite a lot of steps to make an amino acid. We had a protection, to make a peptide, we had a protection step here, 1 protection step, 2 protection steps, and then 3 protection steps. We had 2 deprotection steps, no, actually 3 deprotection steps, and then we had 2 amide bond forming steps. So it's actually quite complicated to make a tripeptide. We just wanted to make these 2 amide bonds, and it took us 8 different steps. And this is okay because the protection reactions are very efficient, close to 100%. But there are some challenges, and we want to talk just briefly about those challenges. We'll go ahead and assume that the protection and the deprotection steps are about 100% yield and no purification is necessary. And with benzyl ester hydrogenolysis and Bach deprotections, that's often true because the only byproducts are actually just sort of solvent molecules. But the coupling steps can be somewhat inefficient. Usually you're using a 1-to-1 ratio of carboxylic acid to amine, and sometimes that yield is not quite 100%. And so sometimes purification is necessary, and you've got to hope that your dipeptide is sufficiently different in properties from your two starting amino acids that the separation by chromatography will be easy. And again, the second coupling reaction, again, is not quite 100%, and some, again, purification is necessary. When you do purification, often you lose a little bit of material. So let's assume that after the coupling steps and purification overall, even though all the protection and deprotection reactions are 100%, let's assume that each coupling step has around 80% isolated yield. That means after purification, that's what we isolate. That means overall yield, assuming everything else but the coupling steps is 100%, overall yield would be 0.8 squared, or in this case, 64% yield. And that might be pretty good. That might be okay. But imagine you wanted to do this not only for to make a tripeptide, but what if you wanted to do a 30 amino acid peptide? Let's consider what kind of yield you could expect, and this is assuming that the purification is easy and that all the coupling steps are equally efficient, which they are not. But let's pretend for now that that's the case. And let's imagine trying to do basically 80% yield to the 30th power. And let's just quick do the math on that to see what we're left with. Okay, that equals 0.001. 2. So you have 0.12% yield. So this method is good for making short peptides, but if you want to make longer peptides, this method is not so good. By the way, the method that we have talked about, where we do all of these reactions in solution, is called solution phase peptide synthesis. And again, solution phase peptide synthesis is great for peptides that are maybe 10 to 15 amino acids long, maybe shorter. And there are some things you can do to increase the yield and make it better. But in general, once you get longer than sort of 10 or 15 amino acids, the method's not that great anymore. And so we'll need to talk about another method that solves this problem, but it looks like we're out of time for today. So I guess I'm calling an audible and going to give one more lecture on peptide synthesis. It'll be called solid phase peptide synthesis, and we'll describe how this is a solution to the problem of yield for making peptides. And then maybe I'll give you an example of a solid phase peptide synthesis that was really very successful and instrumental in fighting HIV until better drugs became available. So with that, I'll end. See you next time. Stay safe, stay healthy, and stay organic. Hey, that's a good sign-off line. Maybe I'll use that.